Hello and welcome. In today's video, we are going to learn about logistic regression, a supervised classification technique. However, in order to understand logistic regression well, I assume that you understand the very basic principle of linear regression, that it follows a straight line principle. What do I mean by a straight line principle? That a linear regression defines a line in 2D space, a plane in 3D space, and a hyperplane in n-dimensional space. And a line is represented by mx plus c, where m denotes the slope, c denotes the intercept. In vector notation, it denotes w transpose x plus c, where w denotes the coefficients and the c or the bias b denotes the intercept there. Okay, with this basic primary notation, I am Saurav Agarwal, you are watching Datahat, Unfolding Mystery, and today we are going to learn about logistic regression. Let us continue. So the agenda for this video holds as: we shall first introduce what logistic regression means, we shall understand some of the challenges of linear regression and why we are using logistic regression in place of linear regression. Additionally, we shall also understand that though the term represents logistic regression, it is primarily used as a classification algorithm. It is not used as a regression algorithm. After that, we shall understand the squashing techniques, the sigmoid, tanh, and ReLU. We shall also understand logloss, which is the loss function used by logistic regression. And finally, we shall summarize and see the code implementation for logistic regression using Scikit-learn in Python. Now understand from this image here. On the left we have linear regression, on the right we have logistic regression. You see, we have data points which are binary classified, or which have two classes, class 1 and class 0. The data points would be denoted something as this in our 2D space. Okay, a linear regression fits a straight line over it, and you see that this straight line passes through our data points. Logistic regression, on the other hand, uses sigmoid in order to fit our data points. Okay, we shall understand why sigmoid is a better choice here in place of a straight line and what are the challenges. So introducing logistic regression, in statistics, the logistic model, also known as the logit model, is a statistical model that models the probability of an event taking place. So what it does is it considers the probability of an event taking place, and based on that probability it assigns the class label. Usually the threshold is considered as 0.5. If the probability is higher than this threshold, then the class label is considered to be positive or 1. However, if the threshold is less than 0.5, it is considered negative or 0. Understand, logistic regression can also be applied to multi-class settings, but the trick there is, in order to apply logistic regression to multi-class settings, we use one versus rest approach. Now what is this one versus rest approach? You take any two classes, say for example you take one class at a time and you consider all the other classes as the others, and you fit a logistic regression model. Again, you repeat the process by taking some other class as a primary class and all the others grouped together. This way you fit a one versus rest model in a multi-class setting for logistic regression. On the right you see there are certain data points. Okay, so we have taken certain data points as x and y. We have class label 0, class label 1. Why we have taken this data is just an example to understand the challenges associated with linear regression and why we should not use linear regression for binary classification, instead use logistic regression. So as you can see from the image here, we have the data points plotted in this graph, in this chart, the green points here. Okay, now your logistic regression model is the first line, which is the blue line here. Okay, it is passing through these data points. Now we take a cutoff, say we take the cutoff at 0.5. Okay, so when the value is 0.5, sorry, when the x value is somewhere around 2.1, your cutoff value is met, and any point to the right of this would be considered class 1 and any point towards the left would be considered class 0. You understand this cutoff? Okay, your threshold is 0.5 here, so cutoff based on this threshold is 2.1. Now what happens? Say for example you have an outlier. Now linear regression is very much prone to outliers. Remember the assumptions that we talked about in linear regression and what are the challenges associated with some of these assumptions? If you haven't watched that video, I'll attach the link in the I button above. Make sure to watch that video after watching this. Okay. Now, if you have an outlier in your data set, your best fit line would tilt towards the outlier. Now, what would happen in this scenario? Now, in this scenario, your best fit line, this blue line, would tilt towards this red line, towards your outlier point here. Okay. Now, what happens in this scenario? Your cutoff value changes. Either you need to reduce your threshold or you need to vary your cutoff. However, this doesn't give you a clear picture of how your data is distributed. It gives you a biased distribution. Rather, it biases your cutoff towards the outliers. Now, if you choose an outlier, say 0.5, right? If you choose an outlier 0.5 in this case, then your cutoff now is 2.8 somewhere. And most certainly some of the positive points which were actually positive would now be classified as negative points because of this margin you are getting now towards the shift. The other thing that you would question is, now what if we change our threshold? You could very well change your threshold. Say now you take your threshold as somewhere around 0.42. Okay, then you would still get the classifications right, but what would happen is the reliability of your models would not be intact and your models would be biased due to the outliers in it. Okay, it would not present the complete picture. Now say for example, if you have an outlier which is very far off, now your best fit line would completely tilt towards that line and most certainly you might not get any appropriate cutoff in that scenario. So your linear regression, when used as a cutoff for a classification setting, is very much prone to outliers, and therefore what we should do, we should clip our values. What we want our values that we get, the outcomes should lie between this class labels. We have two class labels, 0 and 1. So our values should lie between these values 0 and 1. And what other quantity or what other statistical measure lies between 0 to 1? It is none other than probability, right? Now if understand this very clearly. Okay, now your values should lie between 0 and 1. What would happen now is you could consider those values as the probability or the confidence in the outcomes if you are able to clip your values in that range. And you should very well clip the values in that range because your class labels are aligned in that range. You should not try to go far beyond. I'm not saying that it is not possible, but ideally it should be clipped in the range. Now how do you clip these values? This is the primary question that we are going to answer in the coming slides. So as we mentioned that linear regression is impacted by outliers and the best fit line tilts towards the outliers. Okay, yeah. So coming to the squashing. So squashing is a technique which restricts or which constricts your output to a certain range. We primarily talk about three squashing techniques: tanh, sigmoid and ReLU. And these are very popularly used in machine learning and deep learning techniques. Logistic regression uses one of these techniques and we'll talk about it sooner. Okay. First is the sigmoid. As you can see, the graph of a sigmoid function looks something like this. And the functional notation is 1 upon 1 plus epsilon to the power minus x. This is a function of x. Okay. So here you see the values are clipped between 0 to 1. Now this could very well denote the probabilistic outcomes, right? The other one, tanh, you see tanh, the values lie between -1 and 1. Okay, another advantage of using squashing is it allows you to introduce non-linearity in your models. When we shall talk about deep learning, we shall understand why introducing non-linearity is important and how that would help us train our models better. That is primarily dependent on gradient descent, computing the gradients, right? You understand that if a function is differentiable, when that function would be differentiable? If it follows a certain polynomial graph. Even a straight line is differentiable, but many times when you go for complex models, right, you would not have an appropriate straight line. Rather, it would be multiple crossovers of straight lines. So there you would have points where it is not differentiable. So there, using these squashing techniques and introducing non-linearity would help. Now let us come back to the topic again. Let us not go much deeper into it. We'll discuss it when we talk of deep learning. Now coming to our third squashing technique, ReLU. What ReLU does is, it considers the max of 0 and the value itself. So all values towards the left of 0 would be 0, and all values toward the right of 0 would be considered the value themselves. Now again you would say that where is ReLU used, what are the functions, why do we use? We shall discuss. These are primarily used in the deep learning techniques, okay, and we shall not dive deeper as for now. If you really want and curious to learn why and where to use ReLU, I'll attach a link in the description. Go and check that out. Also let me know in the comments if you faced any challenges there. Now logistic regression uses sigmoid squashing technique. You remember, like we talked, it would be ideal to have the values clipped between 0 and 1, and that would denote the probabilistic outcomes. Now logistic regression using sigmoid over our linear regression, let me put it this way. Linear regression, when mixed with squashing technique, that is the sigmoid squashing technique, becomes logistic regression. Okay, this is the simplest understanding. Squashing is used to constrict the outputs to a certain range. We already discussed this. They transform an unbounded margin space to a bounded space. Okay, sigmoids, okay, this might not be 100% true. Say for example, in the case of ReLU, your left boundary is constricted but your right boundary is still unbounded. Sigmoid squashes the unbounded margin space to bounded probability space. This is a sigmoid function. Okay, it would be good if you remember this, but that's fine, right? There are multiple techniques already available, multiple functionalities in the various libraries of Python. You could use that, but it would help you understand things better if you remember this formula. Okay, tan squashes them to -1 to 1 as we already discussed, and ReLU to 0 to infinity. Okay, so you understand the significance of squashing. It will help you constrict your outputs to a range of 0 and 1, which we need for our binary class setting. And this sigmoid squashing technique is used in logistic regression. Now we shall understand the loss function that is used in logistic regression and how this loss function will help us get appropriate results using this sigmoid and whatever backdrop that we discussed so far. So we shall discuss here logloss, which is also known as cross entropy and used as a loss function in classification problems. Logistic regression uses logloss. This is the functional notation. You see, ignore this summation for now, just consider one data point. Okay, this summation is over the entire data points, or say for example you have n data points in a data set, so this summation is over all the points. So you take one point yi denotes the actual value. You take log of the probabilistic outcome that you got from your model, logistic regression model, plus 1 minus yi. Okay, this yi is actual value, log of 1 minus p of yi. We'll understand why we have two components here, but just bear with me for the time being. Okay, this is the functional notation of logloss. P of yi is the probability of getting 1 or getting the positive class, whereas 1 minus p of yi, which is intuitive, right? If the probability of getting 1 is k, the probability of getting 0 is 1 minus k, because it is a binary class setting. Now using the graph, we'll understand how the two components of a logloss will help us formulate our problem. Okay, so one of the components was minus log of hx. This hx denotes p of yi. Okay, and the other component was minus of log of 1 minus hx. Okay, we multiplied it with yi and 1 minus yi, but understand for the timing what the graphs of log of hx and minus of log of hx and minus of log of 1 minus hx denote. So you see, when your actual value is 1, or when your probability, or when your model, logistic regression model, outputs the probability as 1, your log of minus of log of hx becomes 0. Okay, it approaches 0 when your probability for the positive class increases, whereas minus of log of 1 minus hx reaches 0 when the probability of the positive class becomes minimum. Okay, so when, understand this, you have two classes, class 1 and class 0. When your model is giving a very high probability, it denotes that the model is predicting that this should belong to class 1. So in that case, your log of hx would reduce. On the other hand, if your model is giving low confidence, that means it says that this is a 0 class label. When I say low confidence, doesn't mean that the model is less confident in the results. It means it is having a low probability of having class 1. Okay, that denotes it tends to predict class 0. In that case, your other function would tend towards 0. Okay, hope this is clear, hope this is making sense so far. Just let me know in the comments if this section is confusing or if you found any challenge in this. I'll again repeat over this. Okay, let me just go over it once again. We have two components. Say we had two components, this log of p of yi and log of 1 minus p of yi. So we negate both of them. See the negative sign here, we negate both of them. Now these two functions are denoted something as this, and this x-axis denotes your probability of getting class 1 or probability of getting the positive class. So when this probability of getting positive class increases, your first function, the first function reduces, whereas the other function reduces when this probability decreases. Okay, understand this much so far. Now we'll see the certain scenarios. Now say for example, your actual value and the predicted values are same. So your actual value is 1, your predicted value is also 1. What would you want? You would want that your loss should be 0 because your model is giving the right output. Now if your probability, if the probability of the positive class is 1, in this case your loss for this is loss for this is 0, and the loss for this is maximum, infinity. So but what will we want? We want the loss to be 0. We want the overall loss to be 0. So what we have here, we have 1 minus yi multiplied to this component. Remember your yi is 1 because actual value is 1 and your model, and this is 1. So 1 minus 1 0. So this component cancels out altogether. What you are left with is this component. Okay, so this is how it works. When your actual label is 1, you consider the first portion. When your actual label is 0, you consider the second portion. So you are comparing your positive class with the positive class outcomes or probability of getting the positive class, and your negative class or the class 0 with your probability of getting class 0. Okay, simple. You can understand this using some different cases, right? When yi is 0, p of I hat is also 0. In that case again you want your loss to be 0. So the first component, the loss for this component would be very high. So what we are doing, we are multiplying it with yi. Now yi is 0, so this component goes 0, and the other component, your probability of yi is your log is 1 because probability of yi is 0, so this component also goes 0. Your loss becomes 0. The other case is when your actual value is opposite of predicted value. In this case you want your loss to be very high. So the same rules apply. You can just impute the values here and you see what the results are. I give you as an assignment. Okay, let me know in the comments what your results are using the values. And the third scenario is when your predicted probability lies somewhere between 0 and 1. Now in this case, say your probability is 0.6 and your actual class label is 1. So though your model, if you set a threshold of 0.5, though your model would be classified as having actual value, predicted value as 1, but the model is still 0.4 points less in terms of probability, right? Which that 0.4 points is going to the towards the negative class, which you don't want. So you must have a certain non-zero loss in that scenario. So how that would play? Your yi component, log of p of yi would be certain non-zero value, and this component, because your yi is 1, this would be 0. So what your loss would be? Loss would be from this component. However, when your actual class is 0, you would have a certain degree of loss from this particular component. Now you would notice here that in the other component, okay, when your p of yi hat is 0.6, so 1 minus p of yi is 0.4, right? You wanted your actual label to be class 0. Your model predicted 0.6. So the gap is wider as compared when you wanted the model to predict 1 and it predicted 0.6. So there the gap is 0.4. Here the gap is 0.4. So you would say that log of 0.4 is less than log of 0.6. But what do we want here? We want the log of 0.4 to be greater than log of 0.6. Why? Why? Tell me. Because understand, now we are applying a negative sign here. So what would happen? It would reverse the signs. It would reverse the notations. You just plug in the values and you would understand. What do I mean by it? And what I am trying to explain here. It's very easy to understand as you play it down mathematically. If you see yi is 0, p of yi hat is 0.6. Your log of 1 minus p of yi is 0.4, right? You are 0.6 away from your class 0, the class that you wanted to predict, but you are only 0.4 away from a positive class. So when you apply this negative point, you get that difference, right? You get the difference of how far apart your probability is to the actual outcome. Now a small quote for the viewers, the audience to remember: the goal is to turn data into information and information into insight. That is what we as data scientists, that is what you as data science enthusiasts strive to achieve. We want to convert data into information and that information into insights for businesses, for leaders, for various organizations to utilize them and build successful business models, build successful solutions, right? So make sure whenever you look at data, you look at from the perspective of an oil or the perspective of gathering information and then drawing insights. With this, we also come towards the end of our video. We shall discuss the implementation, a very short implementation based on Scikit-learn. Okay, but to summarize things here, linear regression is prone to outliers and does not prove reliable for classification problems, as we saw. Squashing is a technique to minimize the impact of extremes and therefore reduce the effects of outliers. Okay, logistic regression uses logloss. So hope you understood, hope you enjoyed the video till here. And if you're new to the channel, don't forget to subscribe, hit the bell icon, share with your friends and data science enthusiasts. And let us continue with the implementation. Also, there are certain references which I'll attach in the description also. Let me know in the comments if you find additional challenges. Also, if you find additional resources, make sure to attach it for your friends and other data science enthusiasts and help them too. Now coming to the implementation for logistic regression using Scikit-learn in Python, we first import the linear model. Linear model is the library or the submodule containing the linear regression, logistic regression, all the linear models. We also import a sample data set, the iris data set. We are loading this xy, load iris, return xy, it's true. Why? We want both x and y, the data points as well as the class labels. What we are creating? We are creating a logistic regression model, setting the random state to 0. Solver is liblinear. You can play around with solvers, but we'll not go into the details of it for now. Multiclass auto. Now when we set multiclass as auto, what will it do? It will automatically try to determine the number of classes and accordingly adjust. You remember we mentioned that logistic regression uses one versus rest approach in multi-class settings. Okay, so in order for that, it will adjust the model accordingly. We are simply fitting the model on the data set and trying to get the score. Now you can also split the data set into train, test, but here I only wanted to show you the implementation using Scikit-learn, and that is why I did not go into further details. Hope you enjoyed the lecture. Once again, if you are new to the channel, don't forget to subscribe, hit the bell icon, and see you in the next lecture. Have a nice day. Bye bye. Jai Hind.